Okay. So here's the class schedule, and I've updated it. We have been talking about two things recently. S4 classes, and we began talking a little bit about Chapter 4. My intent today is to finish both of those. I did an example with the t-test that we had previously done using S3 classes, but I redid it using S4 classes. And then there's an assignment with S4. Now notice I say S4 assignment draft. And that I put it up there because you could contrast it with what you're doing in S3, but also you could sort of start thinking about that, but I haven't fully checked it out. So later this week I'll put up the final version of that S4 assignment. I have quite a bit between now and Wednesday, so I can't guarantee it will. It may be after Wednesday when I do it, but I will do it later this week. It's basically right, but there are a few things I need to check, and we'll go over it today. So, just to let you know where we're going, my intent was to lightly cover Chapter 4, with some of the basic ideas there. A lot of it is sort of Unix commands and a little bit more esoteric topics that are a bit more advanced than I was intending for this class. I want to go through this quickly because then on Wednesday I want to start Chapter 5, which is on character data, which is important. If you're talking about genomics, you are talking about character data. To do a lot of it, at least. If you're talking about alphabet that has 4 letters in it. Although in proteomics, there are more letters to the alphabet. But basically, there's a lot of character manipulation when you're doing what's called sequence analysis or sequence comparison. So Chapter 5 is where we'll be starting on Wednesday. And I'm going to come back to how you create a package from S3 classes. That will actually be your 4th assignment. And there will be another assignment relating to some combination of Chapter 5 and whatever we can cover in Chapter 8. We're not going to be covering the foreign function interfaces of C and Fortran. If you're interested, you can read it. So that's sort of an outline of where we're going. At this point, it'll be mainly 5, and then the chapter on making our packages will cover enough to do the assignment. But I'm going to give you a handout that's, I think, better. Well, you already have it. It's Alicia's. Has a good explanation of making a package. And then, again, the data technologies in Chapter 8, we're going to cover some of that. That's actually a major component of that's well, not a major component, but it is a component of Staff 623. So, but we'll cover some of the highlights here. So that's where we're going. I first of all want to talk about assignment 3. I wanted to mention one thing about it. So I'm just going to open it here, which will open it locally in our studio. So I'm just opening it locally. I just wanted to discuss a few things. Well, maybe I should knit it. So in terms of, I wanted to mention that, first of all, you do one-way default, which is where most of your code is for computing things. Now, if you go down to the variations, one-way.factor, one-way.formula, in terms of how you manipulate it so you get it in the form that you can call it in a default way. And then you have a relatively simple print method. Now, so basically, the summary.oneway creates a summary object and then you can use a print dot. You could use a print dot summary dot object to actually do the printing. Now the question is, you could also put some computations down here as opposed to up here. So there's a question, do you put all your computations up above, or do you put some of them down in the summary? And that sort of depends on how you want to do it. If you have summary inheriting from the original one way, then any slots you define in the original are available to summary also. And if you look at, for example, if you look at LM, and it has a summary method, you can look at the inheritance hierarchy. But the point is that when you're going to do a summary, you have to have, if you actually write summary and you want to write it as a separate, as a separate object you're going to create, then we could inherit it from the original thing to get those slot values, and you wouldn't have to recalculate everything. In other words, what you're trying to avoid is recalculating the same things. Now, one of the things that I could have done, let's get down to the least squares means, because that becomes an issue, because the idea is that the least squares means comes from one way, not from summary. So in other words, everything you need in least squares means, all those slots have to be computed up in the original one, which means most of the calculations are going to be up there. Now, it is possible that you could have also created LS means, you could create it as a class. You could have had it as a class, and it could have inherited also from the one way. In which case, all the part of the calculations could have been down in least squares itself. Now, you can still put some of the calculations down in least squares, things that are specific to it. But again, you have, it's a question of where you put calculations. Do you put them all up in the top one, which you could pretty much put everything you need. For example, what do you need for the least squares means? Well, you need the sample sizes. And if you assume they're not all equal, in other words, it's a one-way analysis of variance, but the different groups could have different sample sizes. So the sample sizes are n sub I equals 1 to a, where there are a groups. Then I'd have to know all those, because I need those to compute the Fisher's OSDs. You have a term that's like a square root of 1 over n sub I plus 1 over n sub j. So you need to know those. And there's no way to get them down here, because they come from the original data. So they're probably going to have to be computed up in that top part and brought down. If this is a function that is built on that original class, then you're going to have to compute those so that you have them available to you. Otherwise, you have to. Well, of course, you could just bring down the data. If you bring down the data as a slot, then of course you could, but you'd be recomputing it, because you probably had to compute it up in the default. You had to get the n sub i's or the n's in the original default method. So you'd be recomputing it again, which is okay, I guess, but generally speaking, we don't like to do that. You also need the means, which again, if you don't bring them down, you have to recompute. So if you just brought the raw data down to least squares means, you'd have to recompute a lot of things that you've already computed up in default. But you don't have access to them unless you make them a slot. So I'm just thinking sort of a design way, how do you want to do it? So, and that does become a design issue. But as I said, you could have made LS means a class that inherits from the original. That would be another way of doing it. So there are several design choices that you make when you design software. If, in fact, besides the LS means, doing the LSD, the least significant difference, there are many other pairwise comparison methods. There's Tukey's HSD, there's the Hochberg's methods, and so forth. There are tons of these pairwise comparisons. Fisher's LSD is only one of many. So if you were going to, you might want to write a more general method. And in fact, R has a general method called pairwise.t.test that does a bunch of the pairwise test. So when you're doing this, just keep in mind what you need to compute in that top one. At a minimum, you'd have to bring down the data so you can, so you can compute them. If you don't want all those things as slots, you're going to have to bring down the data and you're going to have to recompute them. Does that make sense? And generally speaking, we don't like to recompute things. It's kind of a trade-off. I don't have to recompute them, but if I don't recompute them, I have to store them as a slot. So it's a bit of a trade-off. But okay. So that's due this Friday. I should be able to execute it. At the end, oh, I shut it. Let me. So at the end, I say illustrate it. Now you should actually sort of illustrate all aspects of it and write some explanation. But basically, if you add code here to illustrate what you're doing, I should be able to execute this file and get the HTML file. Now, I may point out to you inefficiencies, but at this point I'm not that concerned about how efficient you are. From past experience, I'll have some students that do a piece that takes that much code and others take that much code. It's just a fact. So efficiency is important. But if it's right, I won't necessarily, unless it's right for the wrong reasons, I probably will not grade that much on efficiency. But think about your code and how you can make it more efficient. Instead of using loops, use apply functions, things like that. Okay. Looping in OR is generally something you don't want to do because you almost never need to do it because you have these other functions like apply. You have apply, you have tapply, sapply. You have these functions that are often much better than writing a loop. Now sometimes you can't avoid it. By the way, when you're doing the least squares means, ideally what I would like to see is a triangle. If you're comparing A to B, A to C, A to D, whatever, B to C, B to D, C to D. If I'm making those comparisons, I can write that as either an upper triangular matrix or a lower triangular matrix. Ideally, what I would like to see are the p-values, because that tells me what's, yeah.
Are you okay with us using pairwise.table instead of doing that all?
Why not?
Are you okay with us using pairwise.table in a compare function versus writing?
Yeah. Yeah, if you're going to, the pairwise.table gives you a lower triangle, right? Yeah. Yeah. But ideally, I'd like to see the p-values. If you take the differences, if you take the differences and you tell me what they're compared against, but the better form is to actually compute the, there are several things you could compute. You could compute the differences, you could actually compute the t-values, or you can compute the p-values. Ideally, what you need to make a conclusion are the p-values, right? Are there any questions on this assignment? Okay. What I want to do next is I'm going to look at, I'm redoing the t-test we did a long time ago using S4 methods. And my intent is hopefully that S4 will become a little bit easier if you look at it in this context. I'll leave this here. So, change courses. That's what you should have downloaded from the web. I'll set the working directory, and let's blow this up a bit. Okay, I'm going to have a class called T-Test4, meaning S4 class. And I used a capital T here to distinguish it from T-Test with a small t. So T-Test4 is a class. And so I'm going to define slots. And this is what you have to be careful about, that we define enough slots. Now in the case of T-Test, we just have 2 samples. Now I would like to be able to use some generic function to not only give it, as 2 samples, but also to give it as a factor and a vector. There are several possibilities, or a matrix. In other words, there are various ways we could do it, which we'll take a look at in a minute. So, so at this point, I'm going to define as the slots, which are given in the representation, we get the slots. And this is what I said for your assignment. You're not doing it this way, but you're doing something. Basically, everything you put in the list that you return as that list becomes a slot with the $sign assignment. And so all of those things become a slot in S3. And you have access to them in this object you return. So then if I, for example, apply ls means to that object, I should be able to compute what I need. But I have to have the correct slots in order to do that. So at any rate, T-test is simply going to be numeric. Degrees of freedom is going to be an integer. And then I have my 2 samples. In this case, I only have 2. Now, this would not be appropriate to do the one-way analysis of variance this way, because you don't know how many samples you have. But here I know I have 2, because it's a 2-sample T-test, right? So now, of course, if you wanted to write it more generally, the T-test built into R lets you do 1 sample or 2 samples. So this wouldn't work for a 1 sample. You could make it work by simply not having data in Y2, but here I'm assuming it's a 2-sample T-test. So both Y1 and Y2 are numeric. They're actually going to be vectors. And then we're going to have a tail area, which is the p-value. And then alpha is going to be, of course, the alpha significance level. And reject is logical. It's either going to be true or false. I'm either going to reject or not. So those are the slots that I define. And there has to be a consistency between what I define here and how I use them as arguments below. And the unit prototype I defined, meaning the initial value, was alpha at 0.05. Now, of course, I actually did it twice, as you'll see, or I could override the 0.05 in the initialized method. So that's how we define the t-test. There's no inheritance here. In other words, I don't have a contains. So I'm not inheriting from anything. So we set the class. Now, when you're actually developing code to do this, those slots, you may get down to, say, ls means or something. You say, oh, I need this. And so you may have to add a slot up here. And that's the same thing with S3. You get down to a particular method you want to add, and either there are several choices you have. You could actually subclass it in some cases, or if it's just going to be a method for this main class, then you're going to need access to the slots to compute things, and you may need to add new slots in order to compute what you need to do. And that was true of the S3 class also, and that was the point I was trying to make. So you may start out defining slots, and then you may discover later on, oh, I have to add a couple to get what I want to compute. Now, I've defined an initialize method. Now you're going to create a new object of t-test4 using the new function, but the new function is actually going to call this initialize. And the initialize is sort of like the default method you define in S3 classes. It's where the computations are actually done. So when I initialize it, I'm actually going, what am I initializing? Well, I'm initializing the slots. Now you notice that the initialize, the arguments, there's one called dot object with a capital O, and then y1 and y2. And I have a comma dot dot dot. That means any other arguments that that sort of get passed along by this function. And then I have alpha equals 0.05. Well, that's not really needed because I put it in prototype. But if you wanted, this would give you the opportunity to change things, including down in my generic functions I could change the alpha level, and it would override the prototype. Now the dot object, you see, when I call a new, I haven't actually created the object yet. Well, I do, but I haven't assigned the slots to it. And so that dot object refers to the object you're creating. So when I call a new function, and I am down here when I have a generic function, I have a function called set generic. Here's a set generic, and then I have set method t-test4. The signature will be numeric and numeric, and I'll get to that. And I use the new here. When I do that, it's going to create a new object of this class t-test4, but it's not fully formed because I haven't assigned the slots yet. And so internally at this point I haven't created it and assigned it. I haven't reassigned it back to a real object, which I could. And since I haven't reassigned it back, I'm going to refer to it internally at this point as dot object. So that's actually the first argument, is the dot object. It's the object I'm trying to create. And then the y1 and y2, which correspond to this generic function. Now the generic function does not have the dot object. You don't need it. That's implicit. It's built in to the initialize method. So the initialize method almost always has a dot object. In fact, it probably does always have it. So I'm defining a function that I'm passing along dot object y1 and y2, which are the two samples, and then alpha equals 0.05, and the test is two-sided lower tail to upper tail. So what I'm going to do here is remember this at. So I have dot object at y1 and dot object at y2. I'm just assigning y1 and y2 to that. That actually defines those two slots, y1 and y2. Okay, so now they're part of this object as a slot. So up here, these are the values that actually appear as slots up here. I could have predefined them as in the prototype, but I have no idea what they are. You could just do it as a numeric vector of length 0. So it would be numeric with a 0. And that's what it is, actually. That's if you actually look at it, inspect it, that's what it is. But I might as well not do anything more than that, because for any given instance, I have no idea what the data is. So I'm not going to give it an initial value. I have no idea what the data is going to be. So I'm not assigning it in the prototype. I actually could have defined the tail area in the prototype, because we do know what those are. I could have defined that in the prototype. because those are fixed. It's two-sided, lower-tailed, or up. This determines what you're doing. A two-sided test, lower-tailed test, or opposite. That's going to be fixed. So I could have defined it in the prototype. And then N1 is the length. N1 is the length of Y1 and N2 is the length of Y2. They don't have to be equal. And then the degrees of freedom, you know, N1 plus N2 minus 2 for the two simple t-tests. So that NDF is degrees of freedom for the test. And I'm going to assign it, I have a slot called D dot F dot. And so I'm going to say dot object at D dot F dot. That defines a slot. I'm going to coerce it to an integer. And the reason is because it is an integer, and I defined it as an integer up here. It must be an integer, or you will get an error. So I coerced it to an integer using as dot integer. And then I'm going to compute the pooled variance. And again, this is kind of a simple example. I'm not assuming that we can do Welch's. In other words, if I test that sigma 1 squared is equal to sigma 2 squared, if I reject, then you can do what's called Welch's test. And if you look at the t-test built into R, in fact, it does that by default. It doesn't assume the variances are equal. And so in this simple example we're not doing that, nor did I have you do it in your S3 class. So if you write a more complicated t-test, you do all these things. So I'm just pulling the variance, N1 minus 1 times the variance of Y1 plus N2 minus 2, N2 minus 1 times the variance of Y2, and that whole sum divided by N1 plus N2 minus 2, or NDF. That computes the pooled variance. And then the t-test is simply the difference in means divided by the square root of this S2 plus 1 over N1 plus 1 over N2. So again, I'm not assuming equal signs. So that computed the t-test, and then I assigned the t-test. I have a slot called t-test right here. The t-stat, t-statistic. So I assign that slot right here, which is this computed t-stat above it. And then in order to compute the tail area, I have a switch based on tests. So match that argument test. And I switch based on that as either two-sided lower tail or upper tail. Or if it's not that, it's a warning telling you you have an error. Okay. And then what I'm going to do, I'm computing the p-values there. So if it's two-sided, I'm taking I'm taking the percentage value on the lower end. I'm taking the probability on the lower end after I take the absolute value would be the lower end, and then I subtract it. I subtract that from 1 and then multiply by 2. Or I simply on the lower tail I take the lower end, and for the upper tail I take the upper end. And then the alpha is just alpha, and then the reject is sort of logical. What I just say dot object at tail area, which is the one above it, is less than alpha. So that's either true or false. So in other words, the tail area, which I compute above, it's either, if it's less than alpha, that will be true, and I reject. It's a logical value. And again, I have to be consistent with the fact that I call it logical as a slot. Okay? So, and then I return the object. In other words, the last step is dot object. If that's the return from initialize. So how does this work? Well, let's first of all talk about generic functions in S4. So if I say, I'm going to say set generic to set a generic function, and it's t-test4. I'm going to name it the same as the class. In other words, and that's usually what you do. The generic function is named the same as the class. And I defined it as a function of y1 and y2, again with a two-sample t-test, and we simply say standard generic of t-test 4. And then this allows us to do dispatching just like S3 classes. Now, the difference is that we can dispatch on multiple arguments. And I think there was an example I went through with Frederick Leach's notes on S4 classes where we dispatched on multiple arguments. Whereas in S3, it's almost always dispatched on the first argument. So now I'm going to set 4 methods relating to that generic function, depending on what the first 2 arguments are. So I have y1 and y2, and depending on what type of object they are, I will dispatch separately. So what are my choices? For y1 and y2, they could both be numeric. The first could be a matrix, and now missing is a special thing. It means there is no, you have to put 2 arguments, but in this case, the second argument is missing. Everything is going to be in the matrix. Now this means the 2 samples are going to be the first 2 columns of the matrix, but that implies in this case that the sample sizes are equal. So if I use matrix, I'm putting the data in the first 2 columns. The sample sizes must be equal in that case, because a matrix cannot be jagged, right? So, and then the next one will be a list and missing. Now a list can be jagged. That is, the number of observations in the first sample could be different, and that's the first vector could be different from the second vector of the number. So in this case, I could have unequal numbers. But again, missing is the second argument, because there is no second argument. It's a single list. And then the next one is a factor, which tells the categorical variable, and then the other is the vector. So those are like total n for all the sample sizes. So there's a factor, and then a numeric vector. So those are the 4 possibilities. So that second argument with the C, that's called the signature. I'm going to dispatch on the base of that signature. So when I call t-test 4, I'm going to have one of those 4. But they all get dispatched. But what happens? Well, the only one that calls new is the first one. And that just calls new t-test with y1 and y2. You see, this initialize function only accepts y1 and y2 and their numeric vectors. Well, if they aren't numeric, then I'd have to coerce them, because up here it says they must be numeric. But for 2-sample t-tests, they better be numeric. So this first thing simply says I'm going to give it to 2 vectors separately. And then I'm going to call new with those 2 vectors, and then the initialize method just does its thing. It computes all those slot values. Is that clear? So that's how you do this one. And this is the only one that has a new in it. So if it's the only one that has a new in it, then what's happening? Well, these other ones are calling the one, ultimately we'll call the one that has, it ultimately has to be called, because it's the only place there's a new. So what happens if I have a matrix and a missing? Well, if I have a matrix and a missing, and if I'm assuming the data is in the first 2 columns, where the first group's in column 1 and the second group's in column 2, I'm simply going to subset, I'm going to pick out y, left bracket, square bracket, comma, 1. That picks out in other words, this picks out the first column, and this picks out the second column out of y1. Remember, there is no y2. Okay? But I call t-test of that, but now this has 2 vectors. So what do you think it's called? Well, what this does, since I split up the matrix into 2 vectors, it just calls this one, which calls initialize. Now what about the list? Sort of the same, except that I have double brackets, which gets down to the data. So this gets down to the two real vectors. So again, I have y1 double brackets, which gets down to the raw data, the first vector, and then double bracket 2 gets down to the second one. They don't have to be that's a list with two elements in that list. They do not have, n1 does not have to equal n2 there. So that, again, calls new. And that calls initialize. Okay? So the final one is a factor in numeric. So y1 is the factor, and y2, and y1 has to be the factor because the signature says it's a factor of the numeric. So y1 has to be the factor. So what I'm going to do is get the levels. I'm going to get the levels of y1, and then I'm going to take y2, and I'm going to subset it into two vectors again. And so I say y2, it's going to be subset by y1 equals, double equals, the LAV of 1, the level 1. And so that's going to return a true or false. And everything that's a level 1 will be a true, and everything that's a level 2 or whatever we represent it by will be a false. So that again subsets. And then the same thing for y2, I'm going to subset for level 2's, true and falses. So that gives me the two vectors. And so what do you think now gets called? Okay. So again, what I have is two vectors. So that's going to call this one with the new again. Okay? So, if we represent it in any of those four methods, then this will call the correct thing and we get an object created. Now, I'm going to create a show method, which is like it's like the print. It's a very quick representation. And so, show, I'm going to set a method called show. Show is actually already a generic. But I'm going to, it's a built-in generic. So I say set method show, and that's a method of the t-test4. So the signature here is, in this case, it's saying that it's an object of type t-test4. And so when I show it, I'm just going to print out using cat t-test, and then I'm going to have the t-value. That's going to bring object at t-stat. It will be the slot for the computed t-value. It will print it with a p-value of, and then it prints the object at tail.alpha. I probably should have called that p-value, but at any rate, it prints the p-value. So that's how it prints. It prints my little print prints the t-value and the p-value. That's it. So we know whether or not we reject, but nothing else. Now, at this point, we're going to do a summary method, and I'm going to make it generic. And then I'm going to create a summary method for t-test4. Now, this is the more comprehensive print. Now, I could have, this is a design choice, and I took the simple route. But I could have created summary objects which inherit from the t-test objects. In other words, I could have said set class summary. I could have made summary a class with the summary class inheriting from the t-test. I could have done it that way. That would be another way of doing it. This is basically a more expansive printout that's printing out part of the data. If you look at the code, sample 1, it only prints out the first 5 values. If they're less than 5, it prints everything out. If they're more than 5, it prints the first 5 and puts ... So you can look at the code and sort of, that's what this ... is right here. Because if you've got 100 observations, you don't want to print it all out. I'm trying to give a more complete printout, but not an exhaustive printout. So I do that for sample 1 and sample 2. And then I'm printing out the t-value and the t-area significance level and whether or not you reject or accept the null hypothesis. And then finally, I have a plot method. I don't have an LS means here because only 2. So they're either different or not. So I don't need an LS means type of thing. No, but I'm going to have a plot, which is going to be just a box plot. Again, I made plot generic. Okay, so we could this is an R file that we could actually compute. I'm trying to think. Did I wanted to look here a minute. Yeah, I did a. No, I don't have a .omd for this. I only have this. Whoops, that's what I want to do. So I can source it, and if I source it, I did this, and then I could print out certain things about it, and let's see, what data did I use to did I test this? I thought I tested this with some data. Oh, yeah. I think what I did is, I could say Y1 gets, and I could then say on norm, I could do 10 samples with a mean of 10. Okay. And then I could do Y2 gets on norm. Maybe I have 12 values with a mean of, say, 11. Okay. Then I could try t-test 4 of Y1 and Y2, and that used the show method. That's all we got. But I could also save this in results. And then I could say summary of results. And then that prints out the long method, right? I could say plot results. And it plots the side-by-side box plot. Did I mistype that?
You have Y1.
I have Y1 and Y2. I have Y1 and Y, yeah. Easy way to figure it out when you get something totally unexpected. Notice how the plot worked though. Let me redo this again. By the way, when I redo it, you're going to have new numbers because I didn't set the seed. So let me go back and look at this. Okay, so let's do it this way. Okay. And let me go back. Well, I'll just put results here again. So I'm saving the result. I'm saving the object. So if I type results, I'm just going to get that simple print. But if I do summary again of results, I get the more complete thing, and again the plot, this should show the difference now. If I do the plot of results, I'm going to get something which should be separated out now. So you can see this one's closer to 10 and that one's closer to 11. Now, I should be able to do a couple other things. So it's a little bit harder to create a factor, but I could, for example, say y1 gets a list of y1 and y2, and then I could call t-test 4 based on y1 here, and again it recomputed. In other words, I sent it a list, it split it apart and did the same thing. So, and you could do it with a factor too. You could bring it together as a factor, and that will also work. Are there any questions on this? Now your assignment assignment 3 brought down 2 of them. Very much mirrors your other assignment, but doing S4. So you're going to create S4 classes, and you want a one-way object again. I called it. I actually said define a class one way with a cup. Notice when I say define a class one way with a capital W. Your other assignment didn't have a capital W. I want to distinguish between those two because you don't want them to get mixed up. If they're both defined in a global space, you don't want them conflicted. So that capital W is on purpose. So again, you're going to create a class with the formal slots and maybe prototype. No inheritance at this point. For a one-way ANOVA, just like you did before, except using S4. And so you need the slots of the original data, the between and within sums of squares, between and within degrees of freedom. And I said et cetera because that et cetera kind of depends on what you might compute below. But you're going to have 3 choices here for your generic function, the constructor. You can have since now you have multiple groups, you're going to have a numeric. You're going to have a list of numeric vectors as one choice. You're going to have a numeric vector along with a factor of the same length, and then a data frame with a formula. So you're going to be able to reuse a lot of the code, but it's not a direct one-to-one. In other words, it's not exactly one-to-one. But by doing this, the same problem, I'm hoping you'll see the relationship between an S4 and an S3 class. There is a correspondence. And then 2 is your initialize method. And then you define a standard generic, and then you define methods for each of those 3. And then a show method and a summary method. And then again, LS means. Now again, you could have, both for the summary and LS min, you could have defined those as separate subclasses. I didn't ask you to do that, but you could have defined them as subclasses. And then a plot, and then, so this, if you see, this pretty much one by one mirrors what you had to do in S3. So I'm hoping you kind of get the gist of it by, and also understanding the relationship between the S3 and the S4 classes. So, and any questions on the homework? Okay. I'll put a due date. Again, I may make some modifications to that particular homework assignment. That's basically going to be it. But I haven't checked out all the components of it, so you can look at it, and in particular, if you may want to look at it as you do in the S3 to kind of get an idea of how that's done. But okay. So that'll be your next assignment. By the way, I'm grading these assignments based on 40 points, meaning there'll be, is that right? Yeah, meaning there'll be a total of 5 assignments. If it wouldn't work out that way, we'd prorate it at any rate. But that's my intent. Did they grade that first one as 40 points? Or was it 25? Oh, you're getting them back? You don't have them back yet? I think they are graded. I'll check on it. Okay. So what I want to do now to finish off the time we have left is just look at a few things in Chapter 4. Now, these are some basically the things that we're going to really need for the most part in this chapter are going to be specific things we need in chapters 5 and 8 in particular. And so for that reason, I'm going to go through it, but some of these things are broken. If you run it, you'll see they're broken. They got errors, doesn't find things, you get null returns. The reason is because these are getting in, these are sort of, a lot of these things are accessing the underlying Unix understructure. And depending upon how you set up your machine or the version of Unix you're using, whether we're running something called CentOS, which is a clone of Red Hat, which is an enterprise version, whereas a lot of people run Ubuntu, Linux. And so the way the structure is set up may vary. And therefore, if you give a command that says, you ought to find something here, well, that might be true on the Ubuntu, but it isn't true on the Red Hat. And so, so a lot of these things actually break. So don't be surprised. It's not worth trying to fix them all because this is just looking at some underlying Unix things, and whereas in 5 gets more specific in terms of character manipulation that we actually need. So that's why I'm only going to spend a limited amount of time. And I already spent a few things. So for example, on basic file handling, I mentioned that you know, that I've been giving the command set workspace as the working directory where this file is, and you can see that it's chapter 4. That's the workspace. If I then say get workspace, that gets it. So it looks different because this gives the full path. Notice this tilde. That's relative to my home directory, and that's called the relative path for my home directory. But it's actually the same thing, chapter 4 here and chapter 4 here. They're the same thing. It's just that that is the full path going all the way back to what's called root. And you can see we have network servers, Mozart. Bayes is kind of virtual implementation, and then my account, and so on and so forth. So that goes all the way back to the very first slash, which is root. Now, when I talk about directories, the more familiar name for people that use the graphical interface of the Mac as opposed to the Unix part is folder. And that's true of Windows too. You use the word folder, but a folder is like a directory. One difference between Unix and Windows and the Mac, if you're using the graphical interface part of the Mac, that is that Windows and the graphical part of the Mac are not case sensitive, whereas Unix is case sensitive, just like R. So if you're in the Mac on the terminal, it's case sensitive, but if you're in the graphical interface, it's not. So it's kind of a hybrid. It depends on where you are. Now, most people who use Mac are not at the terminal level, but a lot of the more technical people are, and so. It's actually why a lot of technical people use Macs, because it is Unix underneath, but you can virtualize Windows quite easily, or different versions of Linux. And that's important because if you're testing software, you can be running multiple virtual machines. You can run Mac, various versions of Linux, and Windows, various versions, all at once. So you can actually you can build a workflow where you test your web pages. Perhaps healthcare.gov should have done that. But at any rate, you can actually test your workflow through all these environments. There are system commands in R. sys.file is one of them. And so sys.file is a system command that I'm trying to find from. Now, see, I don't think we're going to find it. Well, we did, I guess. You see, that depends upon whether or not this path is correct. And then we can open a connection, and then we can read lines from it. And then we can close the connection. So F1 is actually the connection that lets me read line by line. For example, using the R command, read lines. Notice the capital L. That's important. So read lines, is a function in R that sort of reads from this open connection. But read lines can read from a lot of things, but in general you have to open a connection and you can read lines and you close the connection. So it's one way you can read a file line by line. Scan is another way, and it can be, so scan actually did the same thing. So there's two ways of reading. Scan just sort of keeps going. You can sort of scan a file. I can find that file.path is a function that finds the directory path to where R resides. I'm sorry, not R, r.home, which is my home for R. And you notice, actually, no, it's the, or I'm sorry, not my home, it's the R home. So you notice that if you wanted to find out where R is, it's in /user live64. That means 64-bit. That's a 64-bit version of R we're running. R and then dot, and that's where you find the R home. Just like you have a home directory. This is R's home directory. And if I want to find where this package is, this package is a subdirectory of R. It's actually, if you look at R, then there's a subdirectory called library, and then under it you find the package. So this gives you a way to find these things. Now, when you install on your local machine, your local laptop, whatever, when you install, if you actually look, the way I usually install, because it's easy, is I go up I usually don't use RStudio. In fact, if you install RStudio, you can install packages, I believe, in RStudio, but it will only install in your local directory, not system-wide. So if I install it, Steve Giesler is the only one that has permission to install it system-wide. That's why I ask him to install packages. But so, for example, if I wanted to install a package, if I go to package installer, and let's say for your homework you want to install Fairway. So if I do a search, so there's that version of Fairway. And you usually want to install the dependencies also. And now notice that there are some choices here at the system level. So if you're on a Mac, you can have multiple accounts on the Mac. And if you saw it at the systems level, anyone who has an account on a particular Mac has access to that package. But if I define it at the, if I say this, then it's at I install it in my path, that is in my home, and no one else that has an account on that machine has access to it. That's what happens if I install software on the RStudio version. I can only install it locally for me, not for you. Steve is the one that can. I mean, I could do it, but I just have him do it. So at any rate, so you could put it in other locations, but you're going to be asked where you want it installed. Okay. There's a default called lib path. So you can install packages in different places. So in particular, now I believe, so you might ask the question, can you install it in both locations, the same package? And the answer is actually yes, you can. So then you might ask the question, well, which one gets used? And I believe the answer is your local one gets used before the system one. I need to check that. I'm pretty sure that's true. Actually, that lib path, I think, might tell you the order. At any rate, so that's how you can install using this. It's very simple to install packages, and actually it's pretty simple. And you can, as I said, you should. I'm pretty sure you can install it in RStudio. It's just that it's only your local account that it gets installed in. Okay, so that's okay. So if I set working directory of our home to be CD, now I'm not sure. Yeah, see this list files path to doc. It's saying that there's nothing there. I'm not sure that's true, and maybe it is. Maybe there is nothing in doc. And also, if you want to know list files where the pattern equals make, again, I don't think there's anything there. Okay. If I set the working directory to doc, this is apparently, this is not giving me permission. If Steve Giesler would give this command, he could do it. And if you do it on your machine, you could do something like this. You can so if I get the working directory, did it change it? What was it before? I'm not sure. Okay. At any rate, I'm not sure these two are in the right place. Yeah, there's nothing there. Okay. So if I say, what I'm going to do now is change back. I'm going to set this file to the working directory, and then I'm going to say list files. So if I say, and then I'm going to say, okay, here are the files X. Okay, these are in here. You notice those are exactly the files down here. But notice that the ones that start with a dot are not listed. It's only, the dot files are called hidden files. And I can list them. So if I go, I forget, where is it? Shell. Okay. So if I do ls, those are, I'm doing ls. Let me say print, this is a Unix command, print working directory, and this says I'm in chapter 4. Okay, that's a Unix command, print working directory. And you can actually call Unix commands within R. You can call ls, for example. ls simply gave a list. Ls stands for list. It lists what's in that directory. I could say ls minus a, and that also lists the hidden files. So if you compare this list to this list, you see that it has the hidden files. So the options are given by a minus sign with an a. Now suppose I say ls minus L. This is the long format. It lists it, but it gives information. It gives the permissions. It gives the files, but it also gives that they belong to me, and I'm in a group called faculty, and it gives the size and the date as modified. It gives the permissions. So I can read and write them, but the group I'm in, or all means the universe, is that it means I have three. This first row, this first column would have, it indicates it's a file, not a directory. And then the next three is read, write, and execute. But execute, these are binary files, they're not executable. So these are read and write. And then this means, the next three means my group, faculty, can read it. And in fact, everyone can read the files. That's assuming you can get into that directory, but the directory may stop you. So just because it says you can read it, doesn't mean you can actually get there to read it. Because one of the execute commands means actually changing directories. Can I get to that directory to actually read it? And you'd have to have permissions to get into the directories before you could even read it, even if you have permissions to read it once you're there. You can combine, if I say ls minus al, that combines the a with the l, and that prints all of the files, including the dot files, in a long format. So you can combine options. The minus AL is combining the A with the L. So Unix is kind of cryptic. Now the reason the Unix is cryptic is because back when Unix was developed, we started using Unix as a department in about 1970. We were very early adopters of Unix. And you had to type, it was just a terminal. No graphical interfaces, nothing. So you had to type everything. So you have to understand, people who used Unix at that time were kind of the geek population. And besides, everything was short. Print working directory, PWD. LS, list. CD, change directory, and so forth. It was very short because that meant you didn't type much. And so this is a Unix shell script I just brought up. I'm going to close that now. How are we doing time-wise? Okay. So at any rate, so you can go down and I don't know if this is actually, so I can read head file. That's a function that actually says read the first. That's a file that says read lines for the first 6 lines by default. Notice it says n equals 6, but you could change that. If I wanted to read the first 10 by default, I could call that function with n equals 10, and it would read the first 10 lines. So these have to do with temporary files. When a lot of programs write temporary stuff out that then gets deleted. It's not files you ever look at. They're sort of cached, or they're temporary files. So if I create a temp file called temp1, and I create another file called temp2, then I could look at temp1, and there's temp1. Notice it just assigned this random set of digits to it. It's not going to stick around. Once I log off, it's gone. It's a temporary file while I have a session. Okay. I think I'm going to skip this next one. This has to do with creating files. And if I look at my home, what's the path name to my home? Did we do this before? So here's my home. That's my path name to my home. Again, I can have file.paths to R, which we've done before, and that's to R. And that, again, gets you to what this is getting to my version of R. It takes my home and adds bin and R to it. So it takes J Harner bin R. In other words, bin means I have some binary files that I've saved under my directory that are not in the whole system directory. Bin stands for binary. So when you typically compile a program, you compile it to a binary file. And so that's a place that I can save my binary files. So if I look at 2R and I say, well, what's the base name of it? The base name is just R, and the directory name goes up to that. So again, these are sometimes you need to pull these things out when you're running Unix. How much time? We're almost out of time. I think I'm going to skip this. You can run through these. You have the file, so you can run through. Some of these may not work now because of the particular structure of our Unix system. I did want to show you, this is important. What are the connections? Well, that last one, it was only there because I ran this code before. The connections, the three you'll typically see is standard input, standard output, and standard error. Standard input is where the input is coming from. Standard output is where it goes by default. And standard error is where the error message is. That if you're compiling code and you make errors, standard output is where it goes. So, for example, in this case, it says there's a terminal for standard for all of these. But notice cal stands for calendar, which we'll get to in a minute. It's a pipe. It's not a terminal. Unix is extremely powerful because of two things that I would say are two of the most powerful: redirection and piping. Redirection says that I can say a file less than something else, and it actually sends that something else into that file. Or I could say greater than means whatever I do here gets sent to this other file. So I'm redirecting the output from one place to another. It may be something that's executable. It gets executed and it sends its result. Instead of sending it to the terminal, you send it to a file. So you have output, and I could run a big batch program. And then I could say greater than some file that I want to save it in. And so that's called redirection. Piping lets you set up a workflow. It's a vertical line. And so a pipe forms a Unix workflow. So I have some Unix command. It gets piped to the next command, gets piped to the next command, and ultimately you may save it in a file with a redirection. So you can build up a workflow. So for example, last semester, when you're doing a big data, one of the main techniques we use is called Hadoop. Hadoop is an open source project of the Apache group. They also make the Apache web service, which drive most of the web servers in the world. Apache is a workflow of a map and phase and a reduce phase. And it's extremely, it's widely used. Now, what the statisticians have done is they've taken the map phase, which are mapping operations, not unlike, remember we defined a map earlier in this course, but we define a map function, or it could be quite complex. And then we have a reduce function. And a lot of statistical operations can be this map reduce. But you can actually connect them with pipes. And so you can build up this workflow. So I can simulate what Hadoop does by this workflow using pipes. Now, the reality is, we had trouble getting a Hadoop server to work last semester when I taught this. And so I actually set up a Unix workflow to simulate it using pipes and redirection. And so it's very, very powerful to do this. Now, big data, as I said, by big data, what do I mean by big data? Let me define big data in the following way. It will not fit in the physical memory of the machine you're working on. No matter how much memory you have, I guarantee you, big data, if you look at data from astronomy, you will never have a machine that is big enough to fit this type of data in main memory. Now, R computes in main memory, so how do we do it? Well, R has lots of ways of doing it, because, at any rate, so those are connections. Capabilities simply show the capabilities of a particular machine you're running on. JPEG, ping, diff, and so forth, tickle, TK. Let's form a text connection. text connection is another type of connection. So I could say, I'm going to form a text connection on letters, and then I'm going to read lines. I'm going to read the first two from ZZ. And then if I show connections, notice that letters is in here now as a connection. Then I could actually scan. Now notice, I've already read A and B, so when I say scan, the next four, it starts with D. So I read the next four. So now I'm at G, right? And now I'm going to push back AABB, and now if I look again, if I scan, it actually pushed those onto the top of the top. So I have AABBGH. And then I'm going to close the connection. And now let's look at the connections again. And notice it's gone. Now, I accidentally did not close this connection called calendar. Okay? And that's why it's there. That's why you should always close your connections. Because otherwise and that was in a previous session. So you should always close these sections. Now, I guess we need to go here. Let's see what time it is. Yeah. You can go, this sync is very interesting. I may show you this next time. Before we had all these nice methods of creating files that I could do a .omw and you can download them and you can re-execute them and so forth. What did I used to do 15 years ago when we didn't have all of these things like .omws, .omds? We didn't have all these ways. Well, we did have a .r file. We could still do that. But there's a command called sync, which captures everything I do. Captures all my commands. So I actually used to lecture and I'd sync it. I'd capture everything, and then I'd unsync it at the end, and I'd have everything I did for class. And I could just do things spontaneously, and it would still catch them. So a sync command is sort of captures the flow. And so that's what's talking about, this text connection sync. It's a type of sync. And here's something on pipes. This is where someplace I form, here's a system command using ls-l. You should go down through these. Someplace I did the calendar. Anyway, I may spend a few more minutes and look for a few important things, but basically I'm going to let you read this chapter. And you can sort of execute some of these and just play around and see what happens. I may spend a few more minutes, but I want to move on to chapter 5. I may pick out a couple more things I'll show you, but then I'm going to do 5. Any questions? Okay. So start reading chapter 5. Just